And so we are happy to have today Francesco Ferraresso with us, who's new here in Cardiff, talking about spectral stability and instability of differential operators on varying domains.
Thank you, Jonathan. It's a pleasure for me to be here giving this talk. And as you said correctly, I will talk about spectral stability and instability of differential operators on varying domains. I would like to say that this is based on some joint works with Jose Arrieta from the University of Madrid and Domenico Lamberti from the University of Padua, that I think is also here, attended the seminar, if I'm not mistaken. I will briefly recall what is the general spectral stability problem on varying domains. I would like to say that, of course, there is a huge literature about this type of problems. So I would just, let's say, make an introduction that is very personal. Probably there are many other results that I will not have time to mention. But after that, I will focus particularly on higher order operators, and the domains will be subject to some kind of boundary perturbations. And after that, I will finally show to you an example of spectral instability that is very typical, and it's related to what is called Dumble domain. So let me get started. So our setting will be the following. Given omega bounded open set in Rn and A alpha betas and L infinity functions satisfying symmetry condition and strong ellipticity, we can define an operator H omega via the quadratic form in this way. And I will assume that the domain of the quadratic form is some subspace of Hm omega that contains Hm0 of omega. These are the standard Sobolev spaces. So if we have some kind of regularity of the boundary, then the spectrum is known to be discrete. And what we would like to know is what happens to the spectrum if we let omega be approximated or be perturbed by a family of domains omega epsilon. And in which sense we are looking at this convergence? Well, we are looking at the so-called compact convergence of the resolvent operators. And this is intended in the sense of Stummel-Vainikko. So basically, we'll now recap a little bit what this means. But the idea is to just look at the resolvent and to try to see if we can prove some sort of pointwise convergence plus compactness property. Just for the notation, I will set omega to be equal to omega 0, H omega epsilon to be equal to H epsilon, and H omega equal to H. So the compact convergence goes like this. So imagine you have a family of Hilbert space H epsilon, and we assume that for every epsilon, there exists some linear map from H0 to H epsilon with the property that the norm of E epsilon F in H epsilon tends to the norm of F in H0 as epsilon tends to 0 for all F in H0. I will refer to this as a connecting system between H0 and H epsilon. This property is somehow a sort of asymptotic isometry property of the family of spaces. And once we have this, we can define what is called the E-convergence. So for every sequence of functions such that every element lies in a different H epsilon, we can define a convergence in this way. So the norm of F epsilon minus E epsilon F0 in H epsilon has to tend to 0 as epsilon tends to 0. And once we have this, we can finally define what the compact convergence is. So a family of bounded operators said to compactly converges to B0 in L of H0 if we have continuity with respect to the E convergence. And for every uniformly bounded sequence in H epsilon, B epsilon F epsilon is pre-compact with respect to the E convergence. And I will denote this by compact convergence with this symbol C. The important thing about this type of convergence is that it is known that in many situations it implies the spectral exactness of the family of operators. So the precise statement is the following. So if we have a family of closed operators, A epsilon, in H epsilon with domain D of A epsilon, and 0 is in the resolvent set of all of them, plus each inverse of A epsilon is compact for all epsilon, and we have compact convergence, then we do know that H1 plus H2 implies the spectral exactness of A epsilon. And this type of results can be found for bounded operators in this article by Vainikko. For more general classes operator in these articles by Stummel, where actually uses a rather different notion that is called discrete convergence, that is somehow equivalent to the E-convergence in many situations, but it has a more general and abstract setting. And Sabine has, that is here, I think, I've seen her before, has an article that appeared in Integral Equation Operator Theory in 2017 about generalization of these properties. So, all right. Now that we have what the compact convergence is, let me move on and let me define what spectral stability is. So this is not, I will say, a general definition, and the nomenclature may change according to different authors. But so if we have this setting here, so H epsilon are positive differential operators defined on some such that the domain of the quadratic form is V of omega epsilon for all epsilon different from 0, while the domain of the limiting operator to the 1/2 is some other, possibly some other space W of omega 0. So we say that the sequence is spectrally exact if it is spectrally inclusive and no spectral pollution appears. This means that every point in the limiting spectrum is approximated by points in the spectrum of the perturbed operators, and every limit point of sequences of spectra, of point of the spectrum of the perturbed operators is actually a point of the limiting spectrum. So this is somehow the classical definition of spectral exactness. On the other hand, I will say that there is spectral stability if, in addition to be spectrally exact, the domain of the quadratic form of the limiting operator is actually equal to V of omega 0. And the point is, there are several examples in which you have spectral exactness, but you don't have spectral stability because W of omega 0 is strictly contained in V of omega 0. Also, let me see. So, yeah, exactly. So, if we are in the setting of the previous slide, so if all the operators have compact resolvent and we have compact convergence of the resolvent operator, then the sequence is spectrally stable if and only if we have this condition because of what we have said before. Okay, so let me recap briefly what happens in some very simple cases. So in the case of the Dirichlet Laplacian, for example, it is really well known, I would say, that the compact convergence is equivalent to the convergence in norm of the resolvent operators that is equivalent to the so-called Moscow convergence of the energy spaces. And this Moscow convergence is defined in this way. So you have two conditions. The first one tells you that every element in the limiting energy space has to be E approximated in the norm V omega epsilon. And every H10D limit point in the weak topology of H10D has to lie in V of omega. The important thing is that since this is an if and only if, basically spectral stability is equivalent to each one of these conditions. However, these conditions are rather, let's say, functional in nature. So in many situations, one would like to have instead a geometric condition on omega epsilon in order to have these conditions.
Francesco,
yes.
Sorry, Francesco, this condition M1, I probably wasn't paying enough attention. Why can you not just take U epsilon to be E epsilon U? Would that not lie necessarily in V of omega epsilon? Is that the deal?
No, it will. Let me see. No, you're right, there is something. No, yes, you're right. So the problem is that E epsilon U will lie in L2 of omega epsilon in general, only in the Hilbert space H epsilon, but it's not supposed to be in V omega epsilon in principle.
Okay, thanks.
So V omega epsilon in general is much smaller. So that's why, yeah,
thanks.
exactly. So I was saying, in general, you may have this kind of functional conditions, but the fact is you would like to have also geometric conditions in many cases. And in the case of the Dirichlet Laplacian, you can, for example, assume that you have some kind of Hausdorff convergence of the open sets plus some kind of uniform regularity on all the sets omega epsilon. And this will imply the Moscow convergence of spaces. This type of results can be, for example, found in these two monographs by Bucura and Buttazzo and by Daniel Dainers. But of course, there are many other papers and books where you can find this type of results in this set. However, as soon as we change the boundary condition, the setting may change completely. And already in the case of the Neumann-Laplace operator, unfortunately, the compact convergence of the resolvents is not equivalent to the norm convergence anymore here. So what happens is that we only have sufficient conditions for the spectral convergence. And for example, there is this paper by Burenkopf and Davies in 2002, where they proved that if you have open sets belonging to the same Lipschitz-Eitels class, and also you want them to be such that it is an interior perturbation, so omega epsilon is included in omega epsilon for all epsilon, and the measure of this difference tends to 0, then you will get compact convergence of the resolvents with quantitative estimates on this difference. However, I have to say, somehow, as soon as you don't assume that you have interior regularity, so some kind, you don't assume this condition here, the setting may become much more complicated. And one of the, let's say, results that you can find is this, in this paper by Arrieta and Carvalho in 2004 in JDE, where they don't assume that the perturbation is interior, and they don't assume a uniform Lipschitz condition. However, in order to make this work, so in order to have compact convergence, they need to assume a rather strange condition. So for every uniformly bounded sequence in H1 of omega epsilon, they need to have that the L2 norm of this function in omega epsilon minus k epsilon, where k epsilon is the shrink of omega 0, has to tend to 0. So somehow this is telling you that if you want compact convergence for the Neumann Laplacian, you cannot allow uniformly bounded sequence in H1 to have L2 mass that accumulates in small portions of omega epsilon, because somehow this omega epsilon minus k epsilon, it is proved a posteriori that it has to tend to 0 in measure if you want to have this condition. So I think this is enough for the Laplace operator. And so this was to show to you what happens for the spectral stability in this, let's say, simple case that is already very complicated. And it is so complicated that there are actually very easy counterexamples to the spectral stability. As, for example, the following one. You can consider the Neumann Laplace operator on the following set. So I think many of you have seen this example already. So you take omega, the unit square in R2, and omega epsilon is the union of omega and this, let's say, mushroom-like perturbation, where this channel has length epsilon and width eta, where eta is much smaller than epsilon. And R epsilon is just a square of edge epsilon, of length epsilon. In this situation, what you get is that the second eigenvalue in omega is strictly positive. However, the second eigenvalue of the whole domain omega epsilon tends to 0 as epsilon tends to 0. So you don't have spectral stability here. And as you can see, this is an exterior perturbation. And this is also violating that Arrieta-Carvalho condition that you had in the previous slide, because somehow you can have accumulation of the L2 mass of some uniformly bounded sequence inside this part here. And so somehow this small part here that is small in measure, it is very important for the energy associated with this problem somehow. All right. So another example of spectral instability that I would like to show is also very classical, but it's a bit different in nature. And it is the following. So this is called the plate paradox or Babushka's paradox from more or less 1960. So if you have a unit ball in R2 that I will denote it by omega, and omega n is a sequence of convex polygons with n edges inscribed in omega, such that omega n converges to omega, let's say pointwise in this sense here, then let us consider on omega n this problem here. This is a problem for the B Harmonic Operator, and is also called the hinged plate model in the sense that it models the vibration of a plate that is hinged at the boundaries. And we define Hn to be the B Harmonic Operator with domain of the quadratic form H2 intersected H10. That is the natural space associated with these two boundary conditions. And H as the limiting operator, we define it with a slightly different domain. So this is the closure of infinity function such that U and Laplacian of U are equal on the boundary in H2. Then what you get is that actually the resolvent of Hn compactly converges to H as m tends to infinity. But it doesn't converge compactly to, let's say, H0, that would be this operator with this domain of the quadratic form. So somehow this is called a paradox, because people doing numerical analysis were trying to approximate the behavior of this problem in the circle by using finite element methods. So they were looking at convex polygons inside omega. And starting from the problem for the hinge plate and considering this sequence of problems, they would not recover the right problem in the limit, but instead they would get another problem where the whole Laplacian of u would be 0 on the boundary. So somehow this is an example where Hn union H is spectrally exact, because you do have spectral convergence, but it's not stable because the domain of the quadratic form associated with H changes in the limit. All right. So after all this brief review, we are more or less at the starting point of our investigation, that was to address the following core problems. So first of all, we would like to find sharp condition on spectral stability for a given operator subject to non-regular perturbations. Because, well, if the perturbation is very regular, there are rather classical results telling you that you will have spectral stability. So we need to go a little bit out of the very smooth setting. And in particular, we are interested in boundary conditions different from Dirichlet or Neumann. This is more because in these cases, there are many results available. So what happens for different boundary conditions, that's much more complicated in general, is not well known. Also, if there are some functional conditions for the spectral stability, we would like to know if there are equivalent geometric conditions, or at least sufficient geometric conditions for the spectral stability. And finally, what happens when we don't have spectral stability? So is it still possible to recover spectral exactness even though spectral stability doesn't occur? And our setting will be the one that I had introduced in the first slide. I will briefly recap here. So we are looking at this problem in the weak form for a given f in L2. And the point is, I don't want to fix v of omega, so I would like to find a criterion that doesn't depend on the particular choice of v of omega in between these two spaces. So we could have Dirichlet boundary condition in this case, we could have Neumann, or we could have intermediate boundary conditions. I will make a further distinction between the so-called strong intermediate boundary conditions and weak intermediate boundary condition, depending on the index of K here. So first of all, we will restrict the possible perturbation of our initial domain omega to domains belonging to the same Atlas class. This is because somehow we would like to do a local argument. And in order to do that, we require that locally, the boundary of omega epsilon, the boundary of omega, can be seen as the subgraph of given Cn function up to, of course, some kind of rotation of this cuboid V. So the picture is more or less like this. You have omega epsilon, you have some kind of cuboid V, and inside this cuboid, G epsilon G looks like the subgraph. yes, omega epsilon omega looks like the subgraph of some function g epsilon g.
Sorry, what does B stand for?
Oh, B stands for bounded.
Thanks.
You're welcome. So the point is, up to a partition of unity, we can actually look locally inside this cuboid at the spectral behavior of these operators. So assume for simplicity that omega is equal to omega intersecting V, and omega epsilon is omega epsilon intersecting V. So if we have, let's say in the general case, then you can recover the general statement by using some kind of partition of unity. Now, it will be clear in a moment what I mean. So the general geometric criterion that we have is the following. So assume that omega and omega epsilon belong to the same CMB atlas class. And assume that V of omega corresponds to intermediate boundary condition for some k in between 1 and n. So if for all epsilon, we have a sequence kappa of epsilon greater than 0 with the following properties. So first of all, kappa of epsilon is bigger than the L infinity norm of the difference between G epsilon and G, and this tends to 0. So this implies that G epsilon has to tend to G in uniform norm. And this is somehow, this is easily seen to be an necessary condition for the spectral stability. And moreover, we have a sort of weighted convergence of the derivatives of G epsilon minus G with respect to this kappa of epsilon that was appearing here. Then what you can prove is that then the resolvent converge compactly. And moreover, these exponents appearing here are actually sharp. So you cannot do better than these exponents. And yeah, so a brief comment about this. The point of this theorem is that the nth derivative, so the highest order derivatives of G epsilon minus G, are allowed to diverge as epsilon tends to 0. Because, for example, when beta equal to m, this kappa of epsilon has a negative exponent here. And depending on what k is, you may have different rate of divergence. And okay, so this theorem was proved in this paper that we published last year in Integral Equation Operator Theory with Domenico Lamberti. And it is based essentially on some other functional criterion that was established in this paper by Arrieta and Lamberti in JDE 2017. So, all right, let me show to you why these exponents are actually sharp. So in order to see that, we need to consider a particular type of perturbation.
Sorry, can you just, just if you can remind what were the G's? Where do the G's come from?
Yes. So, yes. So the G epsilon is the profile function describing the boundary of omega epsilon.
Okay.
And G is the profile function, let's say, describing the boundary of omega.
Okay, thanks.
Of course, if let's say you are in the general situation, so you are not looking at what happens just inside one of those chart V, then here you will have to take the supremum over all this G epsilon J with J that varies inside all the possible V's that are the charts that that cover all of omega epsilon and omega. All right, so I was saying, I would like to show why you have this sharpness here. And in order to show this, we need to work a little bit. So we first consider a specific perturbation that is done by considering oscillating boundaries. So omega now is just, say, an open cuboid. So it's the Cartesian product of an open cuboid of Rn minus 1 and an interval -1, 0. And omega epsilon is this subgraph of this oscillating function where B is periodic, smooth, positive with a given period y, could be, for example, the unit cell in Rn-1. So this function, of course, as epsilon tends to 0, will oscillate quite fast. And on the other hand, it will also tend to 0 with a rate of vanishing that depends on this alpha. So to have a picture in mind, when alpha equal to 1, for example, we have this profile function is tending to 0 quite slowly. Instead, when alpha is equal to 2, it flattens out quite fast. So you see already for epsilon equal to 1/10, we are almost flat. We cannot really see many wiggles here. And so our, let's say, intuition is that in this case, alpha equal to 2, we will have probably spectral stability. And in this case, instead, we will probably not have spectral stability. And actually, this is kind of true, but the story is a bit more complicated. So assume now that H omega epsilon is the polyharmonic operator of order n in omega epsilon. Then, if you look at intermediate boundary condition, alpha has to be greater than n minus k plus 1/2 in order to have compact convergence. And recall that this n minus k plus 1/2 was basically the same exponent we had in the general case for the case in which beta was equal to 0. So this is actually directly related to the general theorem. And for the hinge plate, so the case W22 intersecting W120, this gives alpha greater than 3/2. And the appearance of these 3/2 is, say, something that was kind of known in the literature, even though in a different setting, because in this paper by Mazia and Nazarov, in which they studied the babushka paradox for indented polygons, they found actually a critical exponent that was 2/3. And somehow these two numbers are related because they also have some kind of oscillation of the boundary in the limit. Even though, let's say, this looks all more like an analogy, but I think that the two numbers can be actually be correlated in a clear way. And all right, so this proves that we have spectral stability above this threshold here. What happens if we go below? So I need to define some PD problem before moving on. So we have omega, again, is this cuboid. And in omega, I want to define several different problems. So on all the edges, apart from the upper one, I want to impose what are called strong intermediate boundary conditions. So all the normal derivatives are 0 up to order n minus 2, and then the nth one is equal to 0. On the other edge, the upper one, I have different cases. So I could have Dirichlet. So if all the normal derivatives are 0 up to n minus 1, and I will denote this by h omega d, we could have strong intermediate, so the same boundary condition as here, and then I will denote the operator as h omega s. And finally, we could have what are called strange boundary conditions, in the sense that we have a sort of combination of the previous ones with a factor k appearing here. And I will denote this by h hat omega. And then what you can prove is the following theorem. So if alpha is greater than 3/2, we have spectral stability. This was already proved. I've shown to you before. If we go strictly below 3/2, then the resolvent operator associated to the problem in omega epsilon with strong intermediate boundary condition will converge compactly to the resolvent of H in omega with Dirichlet boundary condition on the upper edge. So we have instability. And finally, if we are sitting on the critical value, we will get a classical homogenization problem in which we'll have the convergence to another operator, h hat omega minus 1, with that strange boundary condition that I've shown to you before. And the factor k appearing in there can be characterized as the energy of some polyharmonic function that is Y-periodic and has a boundary condition that somehow keeps track of how omega epsilon has reached omega. So this B was exactly the profile function of this periodic G epsilon. If you remember, G epsilon was epsilon to the alpha times B of X over epsilon. So somehow to get this result, you need to argue in different ways for each point. And in this case, you really need to work a lot because this is a classical, say, exercise in homogenization theory. You need to somehow rescale to get rid of the periodicity first, then try to find a weak limit. And then you have to try to characterize this extra term, k, that comes out from your weak limit. And well, after some work, you can actually get this. And as a corollary, you get that the polyharmonic operator with strong intermediate boundary condition is spectrally stable if and only if you are above this threshold 3/2. And if you go below, you don't have spectral stability. So this proves the sharpness of the first theorem that I've shown to you. And a similar result holds also for weak intermediate. However, this spectral exactness part here is much more complicated because you don't have just one degeneration, but you have many degenerations. So you can have somehow waterfall of boundary conditions. And according to how alpha is close to 0, you get boundary conditions that are closer and closer to the Dirichlet. All right, so this is more or less what I wanted to do about this geometric criterion. And now I want to show to you instead an example in which our geometric condition doesn't apply. And this condition, this perturbation is the so-called Dumbbell domain. So the Dumbbell problem reads as follows. You consider Dumbbell domains in R2 that looks like this picture. So omega is the union of omega left and omega right. R epsilon is a thin channel with width of size epsilon that connects the two boundary condition, the two smooth domains. And this function G is a C2 and strictly positive. So basically, what we want to do with this Dumbbell domain is to consider a differential operator on it. And it is clear that somehow this channel R epsilon, it looks like it shouldn't have a contribution to the spectrum, because somehow it's gonna vanish as epsilon goes to 0. But on the other hand, the fact that it has or it doesn't have a contribution to the limiting spectrum depends a lot on what type of boundary conditions we are considering. And note, first of all, that this family, omega epsilon, does not belong to any Atlas class. So in particular, we cannot apply the previous geometric criterion. And in the case of the Neumann Laplace operator, the same problem has been considered, and the spectral stability is a kind of delicate problem, because as I said before, the fact that you have or you don't have spectral stability depends a lot on many factors. And in particular, the shape of the channel R epsilon plays an important role. So you can find more about the Neumann Laplacian in these papers. So by Jimbo in 89, Arrieta in 95, and Arrieta, Carvalho, Lozada, Cruz in 2006. So instead, we wanted to look at the Neumann problem for the B harmonic operator. So the Neumann problem looks a bit complicated. Basically, these are the natural boundary condition that comes out when you impose the energy space to be H2. So the weak formulation would read something like this, where d squared here is the Hessian matrix. This means that we are taking the Frobenius product of the Hessian matrices. And well, sigma here is a parameter that is usually called the Poisson coefficient of the plate, that is in between -1 and 1. So I will denote by phi and epsilon lambda of omega epsilon the eigenpairs of this problem. So what can we say about this problem, about the spectral stability? In general, it is not clear. So we need to assume something on the shape of the channel, as I said before. So we assume the following. We would like that H2 omega epsilon uniformly bounded sequences should be approximated by H2R epsilon function with vanish on the junctions. So basically, we would like these two conditions to be satisfied. So V epsilon should approximate U epsilon L2, and the energy associated with V epsilon in R epsilon should be bounded from above by Q of omega epsilon of U epsilon plus a possibly small term vanishing as epsilon tends to 0. So somehow this is a technical condition that is verified whenever the channel has a shape like this. So near the junction, if you have a monotonicity property of the function g, so for example, you know that g is monotonically decreasing close to 0 and monotonically increasing close to 1, then this condition is verified. Of course, this is actually way more general than what I said here, and could be verified also by profile functions that are not really, doesn't have any monotonicity property close to 0 or to 1. Anyway, let's assume now that we have this H condition. So the spectral stability in our case means that the Neumann B harmonic operator in omega epsilon will converge to the Neumann B harmonic operator just in omega without the epsilon. So is this true? Well, it is not, assuming that the H condition holds. So since R epsilon, well, R epsilon is a thin domain, and moreover, one can prove that you have this concentration phenomenon. So basically you have some sequences of functions that are uniformly bounded in H2 with L2 mass that is concentrating in the channel. So because of this, by the Arrieta-Carvalho result, or better, a slight generalization of it, you can prove that you don't have spectral stability. And this implies that you must have some extra eigenvalues in the limit, but then the problem is, how can we characterize these extra eigenvalues? Because somehow this channel is vanishing as epsilon tends to 0. So there is not really a domain on which we can define a problem, a differential problem that gives these eigenvalues. And so this is actually a quite interesting problem. And let me just remark before moving on that the fact that we have spectral instability here is somehow delicate, because if, for example, you assume that you have Dirichlet or intermediate boundary condition on the boundary that is in common between omega epsilon and r epsilon, so this means the upper and lower boundary of the channel, then we would have a spectral stability instead. Why? Well, because if we have a sequence that is uniformly bounded and it is 0 on this part of the boundary, then it follows from Poincare inequality that you can estimate in this way. And this is the first eigenvalue of the Dirichlet Laplacian in R epsilon. So as epsilon tends to 0, since the size of R epsilon is tending to 0, this is divergent. And this implies immediately that the norm for psi epsilon L2 over epsilon has to tend to 0, because this quantity here is bounded, since this energy here is equivalent to the H2 norm, and we have assumed that this H2 norm is uniformly bounded. So because of this, we satisfy the Arrieta-Carvalho criterion, and so we do have spectral stability. Somehow you can also think about this as these extra eigenvalues that could appear that would be given by this Rayleigh quotient. They actually diverge to plus infinity as epsilon tends to 0, so they don't give any contribution in the limit. We don't see them because they disappear at plus infinity. All right, so now finally, can we prove some spectral exactness for the limiting, for some limiting operator H0? And well, we can, but I need to introduce some auxiliary problem. So first of all, this problem here is just the same B harmonic problem with Neumann boundary condition in omega. And this instead is a mixed boundary value problem with Neumann boundary condition on the upper and lower edge of the boundary, and Dirichlet boundary condition on the other edges. So as you can see probably in this picture, you have gamma epsilon is this blue part, and L epsilon is the red part. Okay. So I'm assuming Dirichlet on these sides and Neumann on the others. And then what you can prove is that, first of all, you have an asymptotic spectral decomposition of the eigenvalues. So the eigenvalues of the initial problem, they will converge either to the eigenvalues of the problem in omega or to the eigenvalues of this mixed problem in the channel, in this sense. And by exploiting this asymptotic decomposition, you can actually use again the compact convergence approach. But now the main idea is to change the Hilbert spaces. So instead of consider the same Hilbert spaces, you are now rescaling the part in R epsilon. And you are introducing a limiting Hilbert space that contains also information about the channel with this part here. And then you can define a connecting system, and you can find what the limiting operator is. And this limiting operator looks like a B harmonic operator, more or less, but it is weighted with respect to this G. That was the profile function, and it contains also information about sigma that appears in a rather strange way. And finally, once you have defined, you have done all this work, you can actually prove that you have compact convergence to this H0 in this newly defined Hilbert space. And actually, this compact convergence is even stronger because you can prove it in H2 of omega, not only in L2 of omega. So this sequence is spectral exact, but you don't have spectral stability because, of course, you have extra eigenvalues coming from the segment. So this is where you can find this type of result. Is a paper that we had with Arrieta and Lamberti from IoT 2017. I'm sorry, it went a bit long, I guess. So I would like to end here.
Okay, thank you very much. Are there any questions?
So Francesco,
Yes.
Oh, Leonel's got a question. Go for Leonel first.
Oh, thank you. Why me? Okay. I just have a question. I mean, from in your techniques, the techniques that you use for proving compact convergence, is there any hint on how fast, the speed that the norm of the difference go to zero, say in terms of epsilon and the geometric invariance that you have? Thanks.
Thank you very much. This is a very good question. Of course, we have considered this question, but in general, it is very hard. So for example, in the case of this final example here with the Dumble domain, in the case of the Neumann Laplacian, estimates on the rate of convergence are very well known. And we tried to do the same for the B harmonic, and immediately we got in trouble. And the main problem is you cannot exploit any kind of separational variable. And whenever you have these thin channels, somehow what you're looking for is actually a separational variable to be able to prove some rate of convergence. So I actually don't know. I guess it is feasible in principle, but it is a very hard problem for sure.
Thanks.
Well, it would mean if you want to prove this rate of convergence, you need to carry out some resolvent estimates, norm resolvent estimates, right? And this is always very, very challenging.
Yeah, I don't know actually, because in the case of the Neumann Laplace operator, again on this Dumble domain, you don't have norm convergence. You only have this compact convergence, but still you can prove some somehow, yeah, some rate of convergence estimates. So you can estimate the difference between these two eigenvalues in terms of if I don't remember, yeah, it's epsilon to the 1/2, I think. So of course, it depends on whether you are converging to an eigenvalue that comes from omega, or if you are going to an eigenvalue that comes from the channel. You have two different rates.
Can I ask you a question about, I think it was the main result somewhere on page 15 or so of your talk. The one where you've shown the sharp estimates, right? So I was slightly confused. Yeah, that
here, or maybe
no, the place where your theorems, the statement of your theorem. Yeah, here. So if you in the second part of the statement, the second bullet point, if you take beta equal to 0,
Mm-hmm.
Do I get it right that the power of k epsilon is greater than 1?
So yes. So the
but,
exponent that appears at the denominator, you mean?
Yeah. So does it imply that actually the convergence of the difference between g epsilon and g should be even smaller than in the first assumption, in the first one?
So okay. So from the first condition, you have that kappa epsilon has to be bigger, right, than this difference g epsilon minus g. So the fact that when you put beta equal to 0 there, this means that somehow kappa epsilon has to go like g epsilon minus g to some power that is 1 over n minus k plus 1/2. So a possible choice of kappa epsilon is g epsilon minus norm of g epsilon minus g to the 1 over n minus k plus 1/2.
But this kind of makes a recurrent. I see some kind of contradiction. I don't understand something. For example, if you take m equal to 2 and k equal to 1,
yes,
as an example,
yes,
and you say, okay, the difference between g epsilon and g is, well, you denote this difference by k epsilon, and k epsilon goes to 0. Then you have this second condition, and you say, okay, actually, setting beta equal to 0, you have the difference between g epsilon and g should go to 0 faster than k to the power 3 over 2. And this is a contradiction.
Yeah, I see what you mean, because you want to choose kappa epsilon exactly equal to the uniform norm of the difference between g epsilon and g.
But you don't have to.
You don't have to, exactly. Kappa epsilon here is strictly bigger, and in general it is like g epsilon minus g uniform norm to some exponent that is less than 1. So, and that's why it's not a contradiction, because if you then plug this kappa epsilon in the second equation, then it doesn't give a contradiction if it is strictly bigger.
And then as you differentiate the difference between g epsilon and g, it should converge to 0 slower and slower. That doesn't happen. So
yeah, actually, yeah, exactly. And when beta is equal to n, then these powers are, these derivatives are even allowed to diverge, because when you put n, then of course, yeah.
Yeah. Well, okay. Thanks. Yeah, this is great. Thank you.
No problem.
So Francesco, the question I was going to ask is really about the case where you don't have spectral convergence. So this is probably a way too optimistic question. Is there anything that can be anything useful at all that can be said in those cases about things that are going wrong by using some naive cheap trick, like, I don't know, say in the case of Laplacian, something like Dirichlet-Neumann bracketing, Dirichlet-Neumann bracketing, so bracketing between Dirichlet and Neumann eigenvalues. Is there anything that can be said in general, even very rough?
So you mean, for example, in this example, right? I guess, yeah. Or honestly, I don't know. Probably yes, I would say. Actually, so for example, in this specific example, somehow this is a very mild instability, because if you look at lambda 3 of omega epsilon here, this will actually converge to lambda 2 of omega. Yeah. So somehow, if you rule out this eigenvalue lambda 2 of omega epsilon and you shift the rest of the spectrum by 1, then you will recover the spectral stability. So somehow only this first non-trivial eigenvalue, lambda 2 of omega epsilon, is creating problems. But more in general, I'm not sure, honestly. So I don't know if there is a cheap trick, as you called it, that makes everything clear. But if there is, I'm not aware of it.
Well,
I guess maybe not, because the number of mushrooms that you can attach to the domain can also increase with epsilon.
This for sure,
yeah.
it is a known result. Yeah, if you have a lot of mushrooms, let's say, then you can actually change an arbitrary large number of these eigenvalues. So an arbitrary large number of these eigenvalues will actually tend to 0. Yeah.
Any other questions?
So I have another question, if I may. So how specific are the results to the fact that you consider, say, the biharmonic operators or powers of the Laplacian? So what happens if you add some lower order self-adjoint perturbation in the operator itself?
Okay. So you mean in this final example, right?
For example.
Well,
so instead of the Laplacian squared, you consider Laplacian square plus something lower order, which you can assume self-adjoint.
well, I believe is not. So what
it's not
actually
covered by these results. That's what I was.
So in this result, actually, we proved it, allowing also to have an additional term here that is minus tau Laplacian operator, where this tau is some positive parameter.
Mm-hmm.
And in that case, everything works. Now, if you ask me for a random, let's say lower order perturbation, I believe you need to use some kind of perturbation argument. And well, I'm not so sure because, okay, you would have some relative compactness probably of this lower order perturbation. But I'm not sure because all the spaces are varying. So,
but roughly speaking, you would. I don't expect that you fill the lower order terms because the problem comes from the main term. And I take the chance to say that in this example, there is something strange appearing. And it's not only related to the variation of the boundary conditions, but the equation itself changes in the limit because the parameter sigma, if Francesco, you can show please the limiting equation, you see that the limiting equation is deformed. So basically, if sigma is equal to 0, the Poisson coefficient of the material basically is 0, then no dramatic change in the operator. But if there is some sigma different from 0, then the equation itself in the limit is deformed. And I believe that this has to deal with the mathematical model behind these plates. So because roughly speaking, omega epsilon represents the middle section of the plate, and there is a part which is collapsing, and you would like to say that this is collapsing to a beam, but this is not correct. So yes, that's all.
Well, I don't know if Pierdomenico has answered your question, Matteo, but
Yeah. Thanks.
okay.
Are there any other questions? Okay, if not, then I'll thank Francesco a final time. Stop this.